Artificial intelligence as a scientific discipline has been with us since just after the Second World War. It began, roughly speaking, with the advent of the first digital computers. But I have to tell you that for most of the time until recently, progress in artificial intelligence was glacially slow. That started to change this century. Artificial intelligence is a very broad discipline which encompasses a very wide range of different techniques, but it was one class of AI techniques in particular that began to work this century, and in particular began to work around about 2005. And the class of techniques which started to work at problems that were interesting enough to be really practically useful in a wide range of settings were machine learning. Now, like so many other names in the field of artificial intelligence, the name machine learning is really, really unhelpful. It suggests that a computer, for example, locks itself away in a room with a textbook and trains itself how to read French or something like that. That's not what's going on. So we're going to begin by understanding a little bit more about what machine learning is and how machine learning works. So, to start us off, who is this? Anybody recognize this face? Do you recognize this face?
I do. Is that Alan Turing?
It's the face of Alan Turing. Well done. Alan Turing, the late, great Alan Turing. We all know a little bit about Alan Turing from his code-breaking work in the Second World War. We should also know a lot more about this individual's amazing life. So, what we're going to do is we're going to use Alan Turing to help us understand machine learning. So, a classic application of artificial intelligence is to do facial recognition. And the idea in facial recognition is that we want to show the computer a picture of a human face and for the computer to tell us whose face that is. So in this case, for example, we show it a picture of Alan Turing, and ideally it would tell us that it's Alan Turing. So, how does it actually work? How does it actually work? Well, the simplest way of getting machine learning to be able to do something is what's called supervised learning. And supervised learning, like all of machine learning, requires what we call training data. So in this case, the training data is on the right-hand side of the slide. It's a set of input-output pairs, what we call the training data set. And each input-output pair consists of an input. If I gave you this, and an output, I would want you to produce this. So in this case, we've got a bunch of pictures, again, of Alan Turing, the picture of Alan Turing, and the text that we would want the computer to create if we showed it that picture. And this is supervised learning because we are showing the computer what we want it to do. We're helping it in a sense. We're saying, this is a picture of Alan Turing. If I showed you this picture, this is what I would want you to print out. So there could be a picture of me, and the picture of me would be labeled with the text, Michael Wooldridge. If I showed you this picture, then this is what I would want you to print out. So we've just learned an important lesson about artificial intelligence and machine learning in particular, and that lesson is that AI requires training data. And in this case, the pictures of Alan Turing labeled with the text that we would want the computer to produce. If I showed you this picture, I would want you to produce the text Alan Turing. Okay. Training data is important. Every time you go on social media and you upload a picture to social media and you label it with the names of the people that appear in there, your role in that is to provide training data for the machine learning algorithms of big data companies. Okay? So, this is supervised learning. Now, we're going to come on to exactly how it does the learning in a moment. But the first thing I want to point out is that this is a classification task. What I mean by that is as we show it the picture, the machine learning is classifying that picture. I'm classifying this as a picture of Michael Wooldridge, this as a picture of Alan Turing, and so on. And this is a technology which really started to work around about beginning 2005. It started to take off, but really got supercharged around about 2012. And just this kind of task on its own is incredibly powerful. Exactly this technology can be used, for example, to recognize tumors on X-ray scans or abnormalities on ultrasound scans and a range of different tasks. Does anybody in the audience own a Tesla? A couple of Tesla drivers, not quite sure whether they want to admit that they own a Tesla. We've got a couple of Tesla drivers in the audience. Tesla full self-driving mode is only possible because of this technology. It is this technology which is enabling a Tesla in full self-driving mode to be able to recognize that that is a stop sign, that that's somebody on a bicycle, that that's a pedestrian on a zebra crossing, and so on. These are classification tasks. And I'm going to come back and explain how classification tasks are different to generative AI later on. Okay, so this is machine learning. How does it actually work? Okay, this is not a technical presentation, and this is about as technical as it's going to get, where I do a very hand-wavy explanation of what neural networks are and how do they work. And with apologies, I know I have a couple of neural network experts in the audience, and I apologize to you because you'll be cringing with my explanation, but the technical details are way too technical to go into. So, how does a neural network recognize Alan Turing? Okay, so firstly, what is a neural network? Look at an animal brain or nervous system under a microscope and you'll find that it contains enormous numbers of nerve cells called neurons. And those nerve cells are connected to one another in vast networks. Now, we don't have precise figures, but in a human brain, the current estimate is something like 86 billion neurons in the human brain. How they got to 86 as opposed to 85 or 87, I don't know. But 86 seems to be the most commonly quoted number of these cells. And these cells are connected to one another in enormous networks. One neuron can be connected to up to 8,000 other neurons. Okay, and each of those neurons is doing a tiny, very, very simple pattern recognition task. That neuron is looking for a very, very simple pattern, and when it sees that pattern, it sends a signal to its connections. It sends a signal to all the other neurons that it's connected to. So how does that get us to recognizing the face of Alan Turing? So Turing's picture, as we know, a digital picture, is made up of millions of colored dots, the pixels. Yeah, so your smartphone maybe has 12 megapixels, 12 million colored dots making up that picture. Okay, so Turing's picture there is made up of millions and millions of colored dots. So look at the top left neuron on that input layer. So that neuron is just looking for a very simple pattern. What might that pattern be? It might just be the color red. All that neuron's doing is looking for the color red. And when it sees the color red on its associated pixel, the one on the top left there, it becomes excited and it sends a signal to all of its neighbors. Okay, so look at the next neuron along. Maybe what that neuron is doing is just looking to see whether a majority of its incoming connections are red. Yeah? And when it sees a majority of its incoming connections are red, then it becomes excited and it sends a signal to its neighbor. Now remember, in the human brain, there's something like 86 billion of those, and we've got something like 20 or so outgoing connections for each of these neurons. In a human brain, thousands of those connections. Yeah? And somehow, in ways that, to be honest, we don't really understand in detail, complex pattern recognition tasks in particular can be reduced down to these neural networks. So, how does that help us in artificial intelligence? That's what's going on in a brain in a very hand-wavy way. Okay, so that's obviously not a technical explanation of what's going on. How does that help us in neural networks? Well, we can implement that stuff in software. The idea goes back to the 1940s and two researchers, McCulloch and Pitts, and they are struck by the idea that the structures that you see in the brain look a bit like electrical circuits. And they thought, could we implement all that stuff in electrical circuits? Now, they didn't have the wherewithal to be able to do that, but the idea stuck. The idea's been around since the 1940s. It began to be seriously looked at, the idea of doing this in software, in the 1960s, and then there was another flutter of interest in the 1980s, but it was only this century that it really became possible. And why did it become possible? For three reasons. There were some scientific advances, what's called deep learning. There was the availability of big data, and you need data to be able to configure these neural networks. And finally, to configure these neural networks so that they can recognize Turing's picture, you need lots of computer power. And computer power became very cheap this century. So we're in the age of big data, we're in the age of very cheap computer power, and those were the ingredients, just as much as the scientific developments, that made AI plausible this century, in particular taking off around about 2005. Okay, so how do you actually train a neural network? If you show it a picture of Alan Turing and the output text Alan Turing, what does the training actually look like? Well, what you have to do is you have to adjust the network. That's what training a neural network is. You adjust the network so that when you show it another piece of training data, a desired input and a desired output, an input and a desired output, it will produce that desired output. Now, the mathematics for that is not very hard. It's kind of beginning graduate level or advanced high school level, but you need an awful lot of it. And it's routine to get computers to do it, but you need a lot of computer power to be able to train neural networks big enough to be able to recognize faces. Okay, but basically all you have to remember is that each of those neurons is doing a tiny, simple pattern recognition task. And we can replicate that in software, and we can train these neural networks with data in order to be able to do things like recognizing faces. So, as I say, it starts to become clear around about 2005 that this technology is taking off. It starts to be applicable on problems like recognizing faces or recognizing tumors on X-rays and so on. And there's a huge flurry of interest from Silicon Valley. It gets supercharged in 2012. And why does it get supercharged in 2012? Because it's realized that a particular type of computer processor is really well suited to doing all the mathematics. The type of computer processor is a graphics processing unit, a GPU. Exactly the same technology that you, or possibly more likely your children, use when they play Call of Duty or Minecraft or whatever it is. They all have GPUs in their computer. It's exactly that technology. And by the way, it's AI that made NVIDIA a $1 trillion company, not your teenage kids. Yeah, well, in times of a gold rush, be the ones to sell the shovels is the lesson that you learn there. So, where does that take us? So, Silicon Valley gets excited. Silicon Valley gets excited and starts to make speculative bets in artificial intelligence. A huge range of speculative bets. And by speculative bets, I'm talking billions upon billions of dollars, right? The kind of bets that we can't imagine in our everyday life. And one thing starts to become clear. And what starts to become clear is that the capabilities of neural networks grows with scale. To put it bluntly, with neural networks, bigger is better. But you don't just need bigger neural networks, you need more data and more computer power in order to be able to train them. So there's a rush to get a competitive advantage in the market. And we know that more data, more computer power, bigger neural networks delivers greater capability. And so how does Silicon Valley respond? By throwing more data and more computer power at the problem. They turn the dial on this up to 11. Okay? Just throw 10 times more data, 10 times more computer power at the problem. It sounds incredibly crude, and from a scientific perspective, it really is crude. I'd rather the advances had come through core science, but actually there's an advantage to be gained just by throwing more data and computer power at it. So let's see how far this can take us. And where it took us is a really unexpected direction.